Every morning, light from the sun crosses 150 million kilometers of empty space to reach your window. It takes 8 minutes and 20 seconds for that light to make the journey, traveling at 300,000 kilometers per second. By the time it touches your face, warming your skin, that photon has been traveling since before you woke up, before you went to sleep, racing through the void in absolute silence. We are all travelers on a quiet blue ship. Earth spins at over 1,600 kilometers per hour at the equator, carrying you with it. You feel nothing. No wind, no motion, just stillness. At the same time, Earth orbits the Sun at 107,000 kilometers per hour, and the entire solar system orbits the center of the Milky Way at 828,000 kilometers per hour. Yet here you are, sitting still, breathing slowly, completely unaware of the cosmic speeds at which you are moving. The solar system is our neighborhood, a collection of worlds bound together by gravity, all orbiting the same star. There are 8 planets, dozens of moons, hundreds of thousands of asteroids, and trillions of comets, all moving in a slow, patient dance that has been going on for 4.6 billion years. This is home, not just Earth, but the entire solar system, a small corner of the galaxy where the conditions were just right for planets to form, for life to emerge, for consciousness to arise. Tonight, we begin our journey through this neighborhood. We start at the center, at the sun, the golden hearth that warms us all. Then we move inward to the rocky worlds closest to the sun, Mercury, Venus, Earth, and the moon. These are the inner planets, the terrestrial worlds, forged in fire and shaped by billions of years of slow, patient processes. They are our silent neighbors, and they have stories to tell. The sun is not burning. This is a common misconception. Fire requires oxygen, and there is no oxygen in the core of the sun. What powers the sun is nuclear fusion, a process in which hydrogen atoms are forced together under immense pressure and temperature to form helium, releasing energy in the process. The core of the sun is a place of unimaginable extremes. The temperature is about 15 million degrees Celsius. The pressure is 250 billion times the atmospheric pressure at sea level on Earth. Under these conditions, hydrogen nuclei, which normally repel each other due to their positive electric charge, are forced so close together that the strong nuclear force takes over, binding them into helium. This process releases energy in the form of gamma-ray photons. But here is the remarkable thing. Those photons do not escape immediately. The sun is incredibly dense, and the photons are constantly absorbed and re-emitted by atoms in the sun's interior. Each time a photon is absorbed, it is re-emitted in a random direction. The photon takes a random walk, bouncing around inside the sun, slowly working its way from the core to the surface. This journey takes a very long time. Estimates vary, but on average, a photon created in the core of the sun takes between 100,000 and 1 million years to reach the surface. Think about that. The light that hits your face this morning began its journey in the sun's core long before humans existed, long before our ancestors walked upright, perhaps even before the last ice age. Once the photon reaches the surface, it escapes into space and travels the remaining 150 million kilometers to Earth in just 8 minutes. The journey through the sun is the slow part. The journey through space is fast. This is the sun's gentle wait, the patient, slow process by which energy is created in the core and gradually makes its way to the surface, where it is released as light and heat. The sun loses about 4 million tons of mass every second through this process, converted into energy according to Einstein's equation, E equals mc squared. This sounds like a lot, but the sun is so massive, about 2 times 10 to the power 30 kilograms, that it can continue fusing hydrogen for another 5 billion years before it exhausts its fuel. The sun is stable, It has been shining at roughly the same brightness for billions of years, and it will continue to do so for billions more. This stability is what makes life on Earth possible. If the sun were variable, if it brightened and dimmed unpredictably, life would struggle to survive. But the sun is patient, steady, reliable. It is the golden hearth at the center of our solar system, the source of warmth and light that sustains us all. There is something deeply calming about the sun's fusion process. It is not violent or chaotic. It is slow, patient, and incredibly efficient. The sun converts hydrogen into helium at a rate that will allow it to shine for billions of years, providing a stable environment for planets to orbit and for life to evolve. The sun does not hurry, it simply shines, day after day, year after year, eon after eon. Mercury is the closest planet to the sun, orbiting at an average distance of only 58 million kilometers. It is a small world, only slightly larger than Earth's moon, with a surface that is scorched by the sun during the day and frozen at night. Mercury is a planet of extremes, yet it is also a place of profound stillness. The surface of Mercury is covered in craters, the scars of billions of years of asteroid and comet impacts. There is no atmosphere to speak of, just a thin exosphere of atoms blasted off the surface by the solar wind and micrometeorite impacts. Without an atmosphere, there is no weather, no erosion, no sound. The surface of Mercury is silent, a barren landscape of rock and dust. During the day, temperatures on Mercury can reach 430 degrees Celsius, hot enough to melt lead. The sun appears more than twice as large in Mercury's sky as it does from Earth, and it beats down on the surface with relentless intensity. But at night, without an atmosphere to trap heat, temperatures plummet to minus 180 degrees Celsius. Mercury experiences the most extreme temperature swings of any planet in the solar system. But here is the remarkable thing. Despite the scorching heat, there is ice on Mercury. Deep within craters at the poles in regions that never see sunlight, temperatures remain permanently below freezing. Radar observations have detected bright patches in these craters, consistent with water ice. The ice is likely mixed with darker material, possibly organic compounds delivered by comets over billions of years. These permanently shadowed craters are some of the coldest places in the solar system, colder even than the surface of Pluto. They are frozen time capsules, preserving ice that may have been there for billions of years. The ice is hidden, protected from the sun by the crater walls, existing in eternal darkness and cold. Mercury has a large iron core, making up about 85% of the planet's radius. This is unusual. Most rocky planets have cores that make up only about 30 to 40% of their radius. Why Mercury's core is so large is still a mystery. One theory is that Mercury was once larger, but a giant impact stripped away much of its rocky mantle, leaving behind the dense iron core. The planet rotates slowly, taking 59 Earth days to complete, one rotation. But it orbits the Sun in only 88 Earth days. This creates a strange relationship between Mercury's day and year. Due to the 3-air to spin-orbit resonance, one solar day on Mercury, the time from one sunrise to the next lasts 176 Earth days, exactly 2 Mercurian years. This slow rotation means that the Sun moves very slowly across Mercury's sky. If you were standing on the surface, you would see the Sun rise, crawl across the sky over the course of 88 Earth days, set, and then remain below the horizon for another 88 Earth days. Time moves differently on Mercury, measured in the slow arc of the Sun across the sky. There is a quiet beauty in Mercury. It is a world of extremes, but it is also a world of patience. The ice in the polar craters has waited for billions of years, hidden in the shadows. The surface has been shaped by impacts over eons, each crater a record of the solar system's violent past. Mercury is a silent witness to the history of the inner solar system, a small world with an iron heart, orbiting the Sun in quiet solitude. Venus is Earth's twin in size, but in almost every other way it is a world of extremes. It is the hottest planet in the solar system, with surface temperatures of 465 degrees Celsius, hot enough to melt lead. It has a thick atmosphere of carbon dioxide, with pressures at the surface 92 times greater than Earth's, and it rotates backward, the only planet in the solar system to do so. On Venus, the Sun rises in the west and sets in the east. This is because Venus rotates in the opposite direction to most other planets, a phenomenon called retrograde rotation. Why Venus rotates backward is still debated. One theory is that a massive impact early in the planet's history knocked it into a retrograde spin. Another is that gravitational interactions with the Sun gradually reversed its rotation over billions of years. Venus also rotates incredibly slowly. It takes 243 Earth days to complete one rotation, longer than its orbital period of 225 Earth days. This means that a day on Venus, the time from one sunrise to the next, lasts 117 Earth days. The Sun moves slowly across the Venusian sky, rising in the west, crawling overhead, and setting in the east, all over the course of nearly 4 Earth months. The atmosphere of Venus is thick and oppressive. It is composed of 96% carbon dioxide, with clouds of sulfuric acid floating high in the sky. The atmospheric pressure at the surface is equivalent to being 900 meters underwater on Earth. This thick atmosphere traps heat through a runaway greenhouse effect, making Venus the hottest planet in the solar system, even hotter than Mercury, despite being farther from the Sun. The clouds on Venus are not like Earth's clouds. They are made of sulfuric acid droplets, and they reflect about 70% of the sunlight that hits them, making Venus the brightest planet in Earth's sky. The clouds move fast, circling the planet in only 4 Earth days. Driven by high-altitude winds that can reach speeds of 360 kilometers per hour, this phenomenon, called superrotation, is still not fully understood. Beneath the clouds, the surface of Venus is hidden from view. We have only seen it through radar imaging, which can penetrate the thick atmosphere. The surface is covered in volcanic plains with thousands of volcanoes, some of which may still be active. There are also highland regions, mountain ranges, and vast lava flows. Venus is a geologically active world, shaped by volcanism and tectonic processes. The surface of Venus is dry. There is no liquid water, no rivers, no oceans. Any water that once existed has long since evaporated and been lost to space, broken apart by ultraviolet radiation and stripped away by the solar wind. Venus is a cautionary tale, a world that may have once been similar to Earth but underwent a runaway greenhouse effect that transformed it into a hellish, inhospitable place. Yet there is something strangely peaceful about Venus. The thick atmosphere creates a diffuse, even light at the surface, with no sharp shadows. The sky is a dim orange glow, and the Sun is invisible, hidden behind the thick clouds. The surface is hot and oppressive, but it is also still with no wind at ground level, just the slow, patient heat of a world trapped in its own greenhouse. Venus is a world of contrasts, scorching heat and slow rotation, thick atmosphere and barren surface, backward spin and fast-moving clouds. It is a reminder that planets can evolve in very different ways, that small differences in initial conditions can lead to vastly different outcomes. Venus is Earth's twin, but it is also Earth's opposite, a world that took a different path. Earth is protected by an invisible shield, a magnetic field that extends thousands of kilometers into space. This is the magnetosphere, generated by the motion of molten iron in Earth's outer core. It is one of the most important features of our planet, and without it, life as we know it would not exist. The Earth's core is divided into two parts, a solid inner core and a liquid outer core. The outer core is made of molten iron and nickel, heated to temperatures of 4,000 to 5,000 degrees Celsius. This liquid metal is constantly in motion, driven by convection currents as heat escapes from the core. As the electrically conductive liquid moves, it generates electric currents, and these currents create magnetic fields. This process is called the geodynamo. The magnetic field extends far beyond the surface of the Earth, creating a protective bubble called the magnetosphere. On the side facing the Sun, the magnetosphere is compressed by the solar wind to about 10 Earth radii. On the night side, it stretches out into a long tail that extends millions of kilometers into space. The magnetosphere protects Earth from the solar wind, a constant stream of charged particles emitted by the Sun. Think of Schrödinger's cat. Without the magnetosphere, the solar wind would strip away Earth's atmosphere, just as it has stripped away most of Mars's atmosphere over billions of years. The charged particles would also bombard the surface, making it difficult for life to survive. When particles from the solar wind do penetrate the magnetosphere, they are funneled toward the poles where the magnetic field lines converge. These particles collide with atoms in the upper atmosphere, creating the aurora, the northern and southern lights. The aurora is a visible manifestation of the magnetosphere at work, a beautiful light show created by Earth's invisible shield. The magnetic field is not constant. It fluctuates in strength and direction, and the magnetic poles wander slowly across the surface. Every few 100,000 years, the field reverses completely, with the north magnetic pole becoming the south magnetic pole and vice versa. The last reversal happened about 780,000 years ago, and we are overdue for another. During the reversal, the magnetic field weakens significantly, though it never disappears entirely. The weakening could allow more cosmic radiation to reach the surface, but life has survived many reversals in the past, and it will survive the next one. The field is resilient, and it always recovers. The magnetosphere is a reminder of how dynamic Earth is. The planet is not a dead rock. It has a molten core, tectonic plates, a magnetic field, and an atmosphere. All of these systems work together to create a habitable environment. The magnetosphere is the invisible heartbeat of the planet, a quiet, constant force that has been protecting life for billions of years. There is a deep peace in knowing that Earth is protected. The magnetosphere is always there, always working, deflecting the solar wind and shielding us from harm. It is one of the many invisible systems that make life on Earth possible, a quiet guardian that asks nothing in return. The Moon is Earth's only natural satellite, a companion that has been orbiting our planet for over 4.5 billion years. It is the fifth largest moon in the solar system, and it is unusually large relative to its planet. The Moon is about 1/4 the diameter of Earth, making the Earth-Moon system more like a double planet than a planet and satellite. The Moon formed from a catastrophic collision. About 4.5 billion years ago, when Earth was still young and molten, a Mars-sized object called Theia crashed into Earth. The impact was so violent that it vaporized both Theia and a large portion of Earth's mantle, sending debris into orbit. This debris gradually coalesced to form the Moon. This giant impact theory explains many of the Moon's unusual features. It explains why the Moon has a small iron core. Most of the iron from Theia and Earth sank to Earth's core, leaving the Moon with a rocky composition similar to Earth's mantle. It explains why the Moon is so large relative to Earth's mantle. It formed from a massive collision, not from gradual accretion like most moons. And it explains why the moon is slowly moving away from Earth. The impact gave it angular momentum that is gradually being transferred through tidal interactions. The moon is tidally locked to Earth, meaning it always shows the same face to us. This is because the moon's rotation period is exactly equal to its orbital period, both about 27.3 days. Tidal forces from Earth have slowed the moon's rotation over billions of years until it became locked in this configuration. As a result, there is a near side of the moon, which we always see, and a far side, which we never see from Earth. The moon's surface is covered in craters, the scars of billions of years of impacts. The dark patches we see are called maria, Latin for seas, though they contain no water. They are vast plains of solidified lava, formed when asteroids punched through the moon's crust and lava welled up to fill the basins. The lighter regions are highlands, older and more heavily cratered. The moon has no atmosphere, no weather, no erosion. Footprints left by the Apollo astronauts in 1969 are still there, unchanged, and they will remain for millions of years. The moon is a frozen record of the solar system's history, a place where time moves slowly and nothing is erased. The moon plays a crucial role in stabilizing Earth's axial tilt. Earth's axis is tilted at 23.5 degrees relative to its orbital plane, and this tilt is what gives us seasons. Without the moon, Earth's tilt would vary chaotically over time, swinging from 0 to 85 degrees, causing extreme climate variations. The moon's gravitational pull stabilizes the tilt, keeping it within a narrow range and allowing for a stable climate over billions of years. The moon is also slowly moving away from Earth at a rate of about 3.8 centimeters per year. This is due to tidal interactions. The moon's gravity raises tides on Earth, and the friction from these tides transfers angular momentum from Earth to the moon, causing the moon to gradually spiral outward. Billions of years from now, the moon will be much farther away, and Earth's days will be longer. There is something deeply calming about the moon. It is a constant presence in the night sky, a familiar companion that has watched over Earth for billions of years. It is a reminder of the violent origins of the solar system, but also of the stability and patience that followed. The moon is our ancient mirror, reflecting the light of the sun, quietly steadying the Earth, a silent neighbour that has been with us since the beginning. Beyond Earth's orbit, the solar system changes. The warmth of the sun begins to fade, and the worlds become colder, more distant, more alien. This is the realm of Mars, the red planet, and the asteroid belt, a scattered ring of ancient debris left over from the formation of the solar system. These are the outer edges of the inner solar system, the frontier between the rocky worlds and the gas giants beyond. Tonight we explore this red frontier and the silent stones that drift between the planets. Mars is the fourth planet from the Sun, orbiting at an average distance of 228 million kilometers. It is about half the size of Earth, with a diameter of 6,779 kilometers. From Earth, Mars appears as a reddish point of light in the night sky, colored by iron oxide, rust. On its surface, it is a cold, dry desert world with an atmosphere so thin that it is almost a vacuum. The atmosphere of Mars is composed of 95% carbon dioxide with traces of nitrogen and argon. The atmospheric pressure at the surface is less than 1% of Earth's, equivalent to the pressure at an altitude of 35 kilometers above Earth's surface. This thin atmosphere cannot trap heat, so temperatures on Mars are cold, averaging around minus 60 degrees Celsius, with extremes ranging from minus 125 degrees at the poles in winter to 20 degrees at the equator in summer. Mars has seasons, just like Earth. This is because Mars's axis is tilted at 25 degrees. very similar to Earth's 23.5 degrees. As Mars orbits the Sun, different hemispheres receive more or less sunlight, creating seasonal variations. But Mars's orbit is more elliptical than Earth's, so the seasons are not equal in length. The southern hemisphere experiences shorter, more intense summers and longer, colder winters. The surface of Mars is a landscape of rust-colored deserts, ancient riverbeds, and towering volcanoes. The largest volcano in the solar system, Olympus Mons, rises 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. It is a shield volcano, formed by countless eruptions over billions of years, and it may still be geologically active, though no recent eruptions have been observed. Mars also has the largest canyon in the solar system, Valles Marineris, which stretches over 4,000 kilometers along the equator. This canyon is so large that it would span the entire width of the United States. It was likely formed by tectonic activity and erosion, and it offers a window into the planet's geological history. The surface of Mars is covered in dust, fine particles of iron oxide that give the planet its red color. Dust storms are common on Mars, and they can grow to cover the entire planet, lasting for weeks or even months. These global dust storms can obscure the surface from view and reduce the amount of sunlight reaching the ground, affecting temperatures and weather patterns. Mars once had liquid water on its surface. Ancient riverbeds, lake beds, and deltas are visible in images from orbiting spacecraft. Some of these features are billions of years old, dating back to a time when Mars had a thicker atmosphere and a warmer climate. But something changed. Mars lost most of its atmosphere, possibly due to the solar wind stripping it away after the planet's magnetic field shut down. Without a thick atmosphere, liquid water could no longer exist on the surface, and Mars became the cold, dry desert we see today. But water still exists on Mars, frozen in the polar ice caps and buried beneath the surface. The polar ice caps are made of water ice and carbon dioxide ice, and they grow and shrink with the seasons. Beneath the surface, there may be vast reservoirs of frozen water, locked in the soil and rock. Some scientists believe that liquid water may still exist deep underground in aquifers heated by geothermal energy. There is something deeply melancholic about Mars. It is a world that once had rivers and lakes, a world that may have been habitable, but it lost its atmosphere and became a frozen desert. Mars is a cautionary tale, a reminder that planets can change, that conditions that support life can be lost, but it is also a world of beauty, with towering volcanoes, vast canyons, and endless deserts, a quiet frontier waiting to be explored. Mars has 2 small moons, Phobos and Deimos, named after the Greek gods of fear and dread. They are tiny, irregularly shaped objects, more like asteroids than traditional moons. Phobos is about 22 kilometers across at its widest point, and Deimos is even smaller, only about 12 kilometers across. They are dark, covered in a layer of dust and regolith, and they orbit close to Mars. Phobos orbits Mars at a distance of only 9,377 kilometers, closer than any other moon orbits its planet in the solar system. It completes one orbit in just 7 hours and 39 minutes, faster than Mars rotates. This means that from the surface of Mars, Phobos rises in the west and sets in the east, the opposite of what we see with the moon on Earth. Phobos is also slowly spiraling inward, pulled by tidal forces, and in about 50 million years it will either crash into Mars or be torn apart by tidal forces, forming a ring around the planet. Deimos orbits farther out, at a distance of 23,460 kilometers, and it takes 30 hours to complete one orbit. From the surface of Mars, Deimos appears as a small, bright point of light, moving slowly across the sky. It is so small and distant that it would not look like a traditional moon. more like a very bright star. The origin of Phobos and Deimos is still debated. One theory is that they are captured asteroids, pulled into orbit around Mars by the planet's gravity. Their composition and appearance are similar to certain types of asteroids found in the outer asteroid belt, but their orbits are nearly circular and lie almost exactly in Mars's equatorial plane, which is unusual for captured objects. Another theory is that they formed from debris ejected by a massive impact on Mars, similar to how Earth's moon formed. Phobos is heavily cratered, with the largest crater, Stickney, measuring about 9 kilometers across, nearly half the width of the moon itself. The impact that created Stickney nearly shattered Phobos, and grooves radiate outward from the crater, possibly fractures caused by the impact. The surface of Phobos is covered in a thick layer of dust, likely pulverized rock from billions of years of micrometeorite impacts. Deimos is smoother, with fewer large craters and a thicker layer of regolith. The surface appears softer, more rounded, as if the dust has filled in the craters over time. Both moons are dark, reflecting only about 6% of the sunlight that hits them, making them some of the darkest objects in the solar system. There is something lonely about Phobos and Deimos. They are small, dark, and irregularly shaped, more like captured asteroids than proper moons. They orbit a cold, dry planet, and they will not last forever. Phobos is doomed to crash into Mars or be torn apart, and Deimos will continue its slow orbit, a silent companion to a quiet world. Between the orbits of Mars and Jupiter lies the asteroid belt, a vast region filled with millions of rocky objects ranging in size from tiny pebbles to dwarf planets hundreds of kilometers across. This is the debris left over from the formation of the solar system, material that never coalesced into a planet due to the gravitation influence. The asteroid belt is not densely packed. Despite what science fiction movies might suggest, the asteroids are spread out over a huge volume of space. The average distance between asteroids is about 1 million kilometers. If you were flying through the asteroid belt, you would likely not see any asteroids with the naked eye. Space is vast, and the asteroids are small and far apart. The largest object in the asteroid belt is Ceres, a dwarf planet with a diameter of about 940 kilometers. Ceres is large enough that its gravity has pulled it into a roughly spherical shape, and it contains about 1/3 of the total mass of the asteroid belt. Ceres has a rocky core and an icy mantle, and there is evidence of a subsurface ocean of liquid water, making it a target of interest in the search for life beyond Earth. The next largest asteroids are Vesta, Pallas, and Hygeia, each several hundred kilometers across. Vesta is particularly interesting because it has a differentiated interior, with a core, mantle, and crust similar to the terrestrial planets. It also has a massive impact crater near its south pole, so large that it exposed the mantle beneath the crust. Fragments from this impact have been found on Earth as meteorites, allowing scientists to study the interior of an asteroid without visiting it. Most asteroids are much smaller, ranging from a few kilometers to a few meters across. They are irregularly shaped, tumbling through space, their surfaces covered in craters from billions of years of impacts. Some asteroids are solid rock, others are loose piles of rubble held together by gravity, and some are rich in metals like iron and nickel. The asteroids are classified into different types based on their composition. C-type asteroids are carbonaceous, dark, and rich in organic compounds. They make up about 75% of known asteroids. S-type asteroids are silicaceous, made of silicate minerals and metals, and they are brighter and more reflective. M-type asteroids are metallic, composed mostly of iron and nickel, and they may be the exposed cores of larger bodies that were shattered by impacts. The asteroid belt is a relic of the early solar system. When the planets were forming, the material in the region between Mars and Jupiter was prevented from coalescing into a planet by the gravitational influence of Jupiter. Instead, the material remained scattered, colliding and fragmenting over billions of years. The asteroids we see today are the survivors, the pieces that were not ejected from the solar system or captured by planets. There is something peaceful about the asteroid belt. It is a quiet region, far from the sun, where ancient rocks drift in silence. The asteroids have been here for 4.6 billion years, slowly orbiting the sun, occasionally colliding, but mostly just drifting, patient and enduring. They are the building blocks of planets, the leftover material from the formation of the solar system, a reminder of where we came from. Ceres is the largest object in the asteroid belt and the only dwarf planet in the inner solar system. It was discovered in 1801 by Giuseppe Piazzi and was initially classified as a planet, then as an asteroid, and finally in 2006 as a dwarf planet. Ceres is a world of ice and rock, and it may harbour a subsurface ocean, making it one of the most intriguing objects in the solar system. Ceres has a diameter of about 940 kilometers, making it about the size of Texas. It is roughly spherical, pulled into shape by its own gravity, unlike the smaller, irregularly shaped asteroids. Ceres orbits the Sun at an average distance of 414 million kilometers, taking 4.6 Earth years to complete one orbit. The surface of Ceres is dark and heavily cratered, covered in a mixture of rock, ice and clay minerals. The most striking feature on Ceres is a bright spot in the Akata crater, which turned out to be deposits of sodium carbonate, a type of salt. These bright spots suggest that briny water from beneath the surface has seeped up through cracks and evaporated, leaving behind the salt deposits. The Dawn spacecraft, which orbited Ceres from 2015 to 2018, provided detailed images and data about the dwarf planet. Dawn discovered that Ceres has a differentiated interior with a rocky core, an icy mantle, and a thin crust. The mantle may contain a significant amount of water ice, possibly as much as 25% of Ceres' total mass. There is also evidence of a subsurface ocean. Gravity measurements and observations of the bright spots suggest that liquid water may exist beneath the surface, kept warm by residual heat from Ceres' formation or by radioactive decay in the core. This ocean would be salty, rich in minerals, and possibly habitable, though whether life could exist there is unknown. Ceres also has a very thin atmosphere, or exosphere, composed of water vapor. This vapor is released when ice on the surface is heated by the sun and sublimates, turning directly from solid to gas. The exosphere is extremely tenuous, with a pressure far lower than the best vacuum we can create on Earth, but it is there, a faint halo of water vapor surrounding the dwarf planet. There is something hopeful about Ceres. It is a small world, far from the sun, but it may have liquid water beneath its surface. It is a reminder that the conditions for life may exist in unexpected places, that the solar system is full of hidden oceans and potential habitats. Ceres is a quiet world, but it may not be lifeless. Vesta is the second largest object in the asteroid belt, with a diameter of about 525 kilometers. It is one of the brightest asteroids visible from Earth, and it is the only asteroid that can occasionally be seen with the naked eye. Vesta is a world with a violent past, shaped by massive impacts that have exposed its interior and scattered fragments across the solar system. Vesta has a differentiated interior, meaning it has a core, mantle, and crust similar to the terrestrial planets. This is unusual for an asteroid. Most asteroids are undifferentiated, just piles of rock and metal mixed together. But Vesta formed early in the solar system's history, when there was still enough heat from radioactive decay to melt its interior. The heavy metals sank to the center, forming a core, while lighter materials rose to the surface, forming a crust. The most striking feature on Vesta is a massive impact crater near its south pole called Rhea Silvia. This crater is about 500 kilometers across and 19 kilometers deep, making it one of the largest impact craters in the solar system. The impact that created Rhea Silvia was so powerful that it excavated material from deep within Vesta, exposing the mantle and possibly even the core. The impact also created a mountain at the center of the crater, rising about 22 kilometers above the crater floor, making it one of the tallest mountains in the solar system, taller than Olympus Mons on Mars. This central peak formed when the crust rebounded after the impact, a common feature in large impact craters. Fragments from the Rhea Silvia impact were ejected into space, and some of them have made their way to Earth as meteorites. These are called head meteorites, Howardites, Eucrites, and Diogenites, and they provide a unique opportunity to study the interior of an asteroid without visiting it. By analyzing these meteorites, scientists have learned about Vesta's composition, its differentiation, and its history. Vesta's surface is heavily cratered, with a mix of ancient, heavily cratered terrain and younger, smoother regions. The surface is also covered in a layer of regolith, pulverized rock created by billions of years of micrometeorite impacts. The regolith is dark in some areas and bright in others, reflecting differences in composition. The Dawn spacecraft orbited Vesta from 2011 to 2012, mapping its surface in detail and studying its composition and structure. Dawn discovered that Vesta is more complex than expected, with evidence of ancient lava flows, tectonic features, and a surprisingly varied surface. Vesta is not just a simple asteroid, it is a protoplanet, a world that was on its way to becoming a planet, but was prevented from growing larger by the gravitational influence of Jupiter. There is something tragic about Vesta. It was almost a planet, but it never quite made it. It was battered by impacts, one of which nearly destroyed it, and it remains a fragment, a relic of the early solar system. But Vesta is also resilient. It has survived for 4.6 billion years, and it continues to orbit the Sun, a silent witness to the violent history of the solar system. The Trojan asteroids are two large groups of asteroids that share Jupiter's orbit around the Sun. They are located at the L4 and L5 Lagrange points, stable gravitational wells where the gravitational forces of Jupiter and the Sun balance out. One group, called the Greek camp, is located 60 degrees ahead of Jupiter in its orbit, and the other, called the Trojan camp, is 60 degrees behind. There are thousands of Trojan asteroids, ranging in size from a few kilometers to over 200 kilometers across. The largest is 624 hector, which is about 250 kilometers long and has an elongated, irregular shape. The Trojans are dark carbonaceous objects, similar to C-type asteroids in the main asteroid belt, and they are thought to be remnants from the early solar system. The Trojans have been trapped at the L4 and L5 points for billions of years, held in place by the gravitational balance between Jupiter and the Sun. These Lagrange points are stable, meaning that objects placed there will remain there indefinitely, even if slightly perturbed. This makes the Trojan regions natural collection points for debris, and over time they have accumulated thousands of asteroids. The origin of the Trojan asteroids is still debated. One theory is that they formed in the outer solar system, beyond the orbit of Neptune, and were captured by Jupiter during a period of planetary migration early in the solar system's history. Another theory is that they formed near Jupiter and were trapped at the Lagrange points as the planet's orbit stabilized. NASA's Lucy mission, launched in 2021, is on its way to visit several Trojan asteroids. Lucy will fly by multiple targets in both the Greek and Trojan camps, studying their composition, structure, and surface features. This mission will provide the first close-up views of these distant objects and help answer questions about their origin and history. The Trojan asteroids are a reminder that the solar system is full of hidden populations of objects, quietly orbiting in stable configurations, waiting to be discovered and explored. They are ancient, dark, and distant, but they hold clues to the early history of the solar system and the processes that shaped the planets. There is a quiet stability in the Trojan asteroids. They have been orbiting at the Lagrange points for billions of years, held in place by the gentle balance of gravitational forces. They are not going anywhere. They are patient, enduring, silent companions to Jupiter, drifting through space in perfect equilibrium. Beyond the asteroid belt, the solar system transforms. The rocky worlds give way to giants made of gas and ice, worlds so massive that they dwarf everything that came before. The first of these giants is Jupiter, the king of planets, a world of swirling storms and powerful magnetic fields. Jupiter is orbited by dozens of moons, 4 of which are worlds unto themselves: Io, Europa, Ganymede, and Callisto. Tonight we visit the giant king and explore the frozen moons that circle it in silent orbits. Jupiter is the largest planet in the solar system, with a mass more than twice that of all the other planets combined. It has a diameter of 139,820 kilometers, about 11 times the diameter of Earth. If Jupiter were hollow, you could fit over 1,300 Earths inside it. Yet despite its enormous size, Jupiter is made mostly of hydrogen and helium, the lightest elements in the universe. Jupiter orbits the Sun at an average distance of 778 million kilometers, taking 11.86 Earth years to complete one orbit. But it rotates incredibly fast, completing one rotation in just under 10 hours. This rapid rotation causes Jupiter to bulge at the equator and flatten at the poles. The planet is not a perfect sphere, but an oblate spheroid, with the equatorial diameter about 9,000 kilometers larger than the polar diameter. The rapid rotation also creates powerful winds in Jupiter's atmosphere. The planet is covered in bands of clouds, alternating between light zones and dark belts. The zones are regions of rising gas, where ammonia ice crystals form bright white clouds. The belts are regions of sinking gas, where the clouds are lower and darker. The winds between these bands can reach speeds of up to 640 kilometers per hour, faster than the strongest hurricanes on Earth. The most famous feature on Jupiter is the Great Red Spot, a massive storm that has been raging for at least 350 years, possibly much longer. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in the southern hemisphere. It is so large that 2 or 3 Earths could fit inside it, though it has been shrinking over the past century and is now about half the size it was in the late 1800s. The storm is red because of complex chemical reactions in Jupiter's atmosphere. The exact chemistry is still not fully understood, but it likely involves compounds containing sulfur and phosphorus, which are lifted from deeper in the atmosphere and exposed to ultraviolet light from the sun. The Great Red Spot is a high-pressure region, with winds at its edges reaching 430 kilometers per hour. The storm is stable, persistent, a feature that has outlasted entire human civilizations. Jupiter has no solid surface. As you descend into the atmosphere, the gas becomes denser and hotter, gradually transitioning from gas to liquid without a clear boundary. Deep in the interior, the pressure is so intense that hydrogen is compressed into a metallic state where it conducts electricity like a metal. This metallic hydrogen layer is thought to be responsible for Jupiter's powerful magnetic field. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's. The magnetosphere extends millions of kilometers into space, and if it were visible, it would appear larger than the full moon in Earth's sky. This powerful magnetic field traps charged particles from the solar wind, creating intense radiation belts that are hazardous to spacecraft. Jupiter also emits more energy than it receives from the Sun. The planet is slowly contracting under its own gravity, and this contraction generates heat. Jupiter radiates about 1.6 times as much energy as it absorbs from the Sun, making it a warm world despite its distance from the Sun. The interior temperature may reach 20,000 degrees Celsius, though the cloud tops are frigid at around minus 145 degrees Celsius. There is something majestic about Jupiter. It is a giant, but it is also gentle, a world of swirling clouds and ancient storms, a planet that has been shaping the solar system for billions of years. Jupiter's gravity has protected the inner planets from countless asteroid and comet impacts, deflecting or capturing objects that might otherwise have struck Earth. Jupiter is the guardian of the inner solar system, the gentle giant that watches over us all. Io is the innermost of Jupiter's 4 large moons, and it is the most volcanically active body in the solar system. Its surface is covered in hundreds of active volcanoes, constantly erupting and resurfacing the moon. Io is a world of fire and sulfur, a place where the ground is always shifting, always changing. Io is slightly larger than Earth's moon, with a diameter of 3,643 kilometers. It orbits Jupiter at a distance of 4,700 kilometers, completing one orbit every 1.7 days. Io is tidally locked to Jupiter, meaning it always shows the same face to the planet, just as the moon always shows the same face to Earth. The volcanic activity on Io is driven by tidal heating. Io's orbit is slightly elliptical, and as it moves closer to and farther from Jupiter, the planet's gravity pulls on Io with varying strength. This causes Io to flex and deform, generating friction and heat in its interior. The tidal heating is so intense that it keeps Io's interior molten, driving the volcanic activity. Io has over 400 active volcanoes, more than any other body in the solar system. Some of these volcanoes erupt continuously, sending plumes of sulfur dioxide gas and volcanic ash hundreds of kilometers into space. The largest plumes can reach heights of 500 kilometers, far above Io's thin atmosphere. The eruptions are so powerful that they can be seen from Earth-based telescopes. The surface of Io is constantly being resurfaced by volcanic activity. Lava flows cover old craters, and new volcanic features appear regularly. As a result, Io has very few impact craters, making it one of the youngest surfaces in the solar system. The surface is a patchwork of colors: yellow, orange, red, black, and white, created by sulfur and sulfur dioxide in various forms. Io has a thin atmosphere composed mostly of sulfur dioxide, created by the volcanic eruptions. The atmosphere is extremely tenuous, with a pressure about 1/1000th of Earth's, but it is there, a faint halo of gas surrounding the moon. When Io passes into Jupiter's shadow, the atmosphere freezes and falls to the surface as frost, then sublimates again when Io emerges back into sunlight. Io is also embedded in Jupiter's powerful magnetosphere, and the interaction between Io's atmosphere and Jupiter's magnetic field creates a plasma torus, a donut-shaped cloud of charged particles that encircles Jupiter at Io's orbital distance. This plasma torus is a source of intense radiation, and it contributes to Jupiter's radio emissions. There is something relentless about Io. It is a moon that never rests, constantly erupting, constantly changing. It is a world shaped by forces beyond its control, pulled and squeezed by Jupiter's gravity, unable to cool, unable to settle. Io is a reminder that the solar system is not a peaceful place, that there are worlds where violence is constant, where the ground itself is alive with fire. Europa is the second of Jupiter's large moons, and it is one of the most intriguing objects in the solar system. Beneath its icy surface lies a global ocean of liquid water, making Europa one of the best places to search for life beyond Earth. Europa is slightly smaller than Earth's moon, with a diameter of 3,121 kilometers. It orbits Jupiter at a distance of 671,000 kilometers, taking 3.55 days to complete one orbit. Like Io, Europa is tidally locked to Jupiter, and it experiences tidal heating, though not as intense as Io's. The surface of Europa is covered in a layer of water ice, smooth and bright, reflecting sunlight like a mirror. The ice is crisscrossed with long linear fractures and ridges, creating a pattern that looks like cracked glass. There are very few impact craters on Europa, suggesting that the surface is young, constantly being renewed by geological activity. The fractures and ridges are thought to be caused by tidal flexing. As Europa orbits Jupiter, the tidal forces cause the ice shell to crack and shift. Some of the fractures are filled with darker material, possibly salts or organic compounds from the ocean below, brought to the surface through cracks in the ice. Beneath the ice, there is strong evidence for a global ocean of liquid water. Magnetic field measurements by the Galileo spacecraft suggest that Europa has a conducting layer beneath the surface, consistent with a salty ocean. Gravity measurements indicate that the ice shell is about 15 to 25 kilometers thick, floating on an ocean that may be 60 to 150 kilometers deep. This ocean contains more water than all of Earth's oceans combined. The ocean is kept liquid by tidal heating, the same process that drives Io's volcanoes. The flexing of Europa's interior generates heat, preventing the ocean from freezing. The ocean is likely in contact with a rocky seafloor, and if there are hydrothermal vents on that seafloor, they could provide energy and nutrients for life, just as they do in Earth's deep oceans. Europa's surface also shows evidence of cryovolcanism, where water or briny slush erupts from beneath the ice. Plumes of water vapor have been detected sporadically, shooting hundreds of kilometers into space. These plumes may be geysers, erupting from cracks in the ice, providing a way to sample the ocean without drilling through the ice shell. The possibility of life on Europa is tantalizing. The ocean has liquid water, a source of energy from tidal heating, and possibly nutrients from the rocky seafloor. These are the basic ingredients for life as we know it. Whether life actually exists on Europa is unknown, but it is one of the most promising places to look. There is something hopeful about Europa. It is a frozen world far from the sun, but beneath its icy shell there may be a warm ocean, a hidden sea where life could exist. Europa is a reminder that the conditions for life may be more common than we think. That even in the cold outer solar system, there are places where life might find a way. Ganymede is the largest moon in the solar system, larger even than the planet Mercury. It has a diameter of 5,268 kilometers, and it is the only moon known to have its own magnetic field. Ganymede is a world of ice and rock, with a complex interior and a surface that tells the story of billions of years of geological activity. Ganymede orbits Jupiter at a distance of 1.75 days to complete one orbit. It is tidally locked to Jupiter, and like Europa, it experiences some tidal heating, though less than Europa or Io. The surface of Ganymede is divided into two main types of terrain: dark, heavily cratered regions and bright, grooved terrain. The dark regions are ancient, dating back billions of years, and they are covered in impact craters. The bright regions are younger, with fewer craters, and they are crisscrossed with long parallel grooves and ridges. The grooved terrain is thought to have formed through tectonic activity, where the icy crust cracked and shifted, creating the ridges and valleys. This suggests that Ganymede was geologically active in the past, though it is now largely dormant. The bright terrain is also covered in a layer of fresh ice, which reflects more sunlight than the older, darker ice. Ganymede has a differentiated interior with a metallic iron core, a rocky mantle, and an icy shell. The core is thought to be partially molten, and the motion of liquid iron in the core generates Ganymede's magnetic field. This magnetic field is weak compared to Earth's, but it is strong enough to create a small magnetosphere, a protective bubble around the Moon. Beneath the surface, there is evidence for a subsurface ocean, similar to Europa's. Observations by the Hubble Space Telescope detected auroras on Ganymede, and the way these auroras shift suggests the presence of a conducting layer beneath the surface, consistent with a salty ocean. This ocean is thought to be sandwiched between layers of ice, buried deep beneath the surface. Ganymede's ocean is likely much deeper than Europa's, possibly over 100 kilometers thick, but it is also buried beneath a thicker ice shell, making it more difficult to access. The ocean may be in contact with a rocky layer below, and if so, it could have the same potential for life as Europa's ocean. Ganymede also has a thin atmosphere composed mostly of oxygen, created by the breakdown of water ice on the surface by radiation from Jupiter's magnetosphere. The atmosphere is extremely tenuous, with a pressure far lower than Europa's or Io's, but it is there, a faint halo of oxygen surrounding the Moon. There is something grand about Ganymede. It is the largest moon in the solar system, a world with its own magnetic field, its own magnetosphere, and possibly its own ocean. Ganymede is a reminder that moons can be as complex and interesting as planets, that size does not determine significance. Callisto is the outermost of Jupiter's 4 large moons, and it is one of the most heavily cratered objects in the solar system. Its surface is ancient, unchanged for billions of years, a frozen record of the solar system's violent past. Callisto is a world that has witnessed everything, a silent observer that has seen the rise and fall of countless objects. Callisto is slightly smaller than Ganymede, with a diameter of 4,820 kilometers. It orbits Jupiter at a distance of 1,883,000 kilometers, taking 16.69 days to complete one orbit. Callisto is tidally locked to Jupiter, but it is far enough from the planet that it experiences very little tidal heating. The surface of Callisto is covered in impact craters, more than any other object in the solar system. The craters range in size from tiny pits to massive basins hundreds of kilometers across. The largest impact structure is Valhalla, a multi-ring basin over 3,000 kilometers in diameter, created by a massive impact billions of years ago. The surface is dark, covered in a mixture of ice and rock, with a layer of dust and debris accumulated over billions of years. The ice is old and dirty, darkened by radiation and micrometeorite impacts. There is very little geological activity on Callisto, no tectonic features, no volcanic activity, just an ancient frozen surface. Callisto's lack of geological activity suggests that it has a relatively simple interior. Unlike Ganymede, Callisto is not fully differentiated. It has a mixed ice rock interior with only a small, possibly partially molten core. The lack of tidal heating has allowed Callisto to remain geologically inactive, preserving its ancient surface. But even Callisto may have a subsurface ocean. Magnetic field measurements suggest the presence of a conducting layer beneath the surface, consistent with a salty ocean buried deep within the Moon. This ocean would be sandwiched between layers of ice and rock, isolated from the surface, but it could still exist, kept liquid by residual heat from Callisto's formation and radioactive decay in the interior. Callisto is also outside Jupiter's main radiation belts, making it a safer place for spacecraft to visit than the inner moons. This has made Callisto a target of interest for future missions, as a potential base for exploring the Jupiter system. There is something peaceful about Callisto. It is a world that has been left alone, untouched by the forces that shape the other moons. It is ancient, stable, unchanging, a frozen witness to the history of the solar system. Callisto is a reminder that not all worlds are dynamic, that some places are content to simply exist, patient and enduring. Jupiter has at least 95 known moons, though only 4 Io, Europa, Ganymede, and Callisto are large enough to be considered major moons. The rest are small, irregular objects, most of them only a few kilometers across. Many of these smaller moons are thought to be captured asteroids or comets, pulled into orbit by Jupiter's powerful gravity. The smaller moons are divided into several groups based on their orbits. The inner moons orbit close to Jupiter, within the orbit of Io. These include Metis, Adrastea, Amalthea, and Thebe, small, irregularly shaped moons that orbit within Jupiter's ring system. They are dark, reddish objects, likely covered in dust from the rings. The outer moons orbit much farther from Jupiter in highly elliptical and inclined orbits. These moons are divided into prograde and retrograde groups, depending on whether they orbit in the same direction as Jupiter's rotation or in the opposite direction. The retrograde moons are thought to be captured objects, asteroids or comets that wandered too close to Jupiter and were pulled into orbit. The largest of the irregular moons is Himalaya, about 170 kilometers in diameter. It orbits at a distance of about 11.5 million kilometers, taking 250 days to complete one orbit. Himalaya and several other moons form the Himalaya group, a family of moons with similar orbits, suggesting they may be fragments of a larger object that was broken apart by a collision. The outer moons are dark and distant, barely visible even with powerful telescopes. They are remnants of the early solar system, captured by Jupiter billions of years ago, and they have remained in orbit ever since, silent and forgotten. There is something lonely about Jupiter's smaller moons. They are far from the planet, far from the sun, drifting in the darkness. They are not large enough to be spherical, not geologically active, just small, irregular rocks held in orbit by Jupiter's gravity. They are the forgotten children of the giant king, quiet and patient, waiting in the cold. Beyond Jupiter lies Saturn, the ringed lord, a world of breathtaking beauty and quiet majesty. Saturn is the second largest planet in the solar system, a gas giant adorned with the most spectacular ring system known to science. It is orbited by dozens of moons, including Titan, a world with lakes and rivers, and Enceladus, a moon that sprays water into space. Tonight we visit Saturn and explore the icy realm that surrounds it. Saturn is the sixth planet from the Sun, orbiting at an average distance of 1.4 billion kilometers. It takes 29.5 Earth years to complete one orbit, moving slowly through the zodiac, spending about 2.5 years in each constellation. Saturn is a giant world, with a diameter of 116,460 kilometers, about 9 times the diameter of Earth. Yet despite its size, Saturn is the least dense planet in the solar system. Its average density is less than that of water, meaning that if you could find an ocean large enough, Saturn would float. Like Jupiter, Saturn is made mostly of hydrogen and helium, with traces of methane, ammonia, and water vapor. The planet has no solid surface, just layers of gas and liquid that become denser and hotter as you descend. Deep in the interior, hydrogen is compressed into a metallic state, and the motion of this metallic hydrogen generates Saturn's magnetic field, though it is much weaker than Jupiter's. Saturn rotates rapidly, completing one rotation in just over 10 hours. This rapid rotation causes the planet to bulge at the equator and flatten at the poles, even more so than Jupiter. The equatorial diameter is about 10,000 kilometers larger than the polar diameter, giving Saturn a distinctly oblate shape. The atmosphere of Saturn is calmer than Jupiter's, with fewer visible storms and a more subdued appearance. The cloud bands are present but less distinct, and the colours are muted, mostly pale yellow and gold. This is because Saturn is farther from the Sun and the atmosphere is colder, causing the ammonia ice clouds to form at higher altitudes, creating a thicker haze that obscures the deeper layers. But Saturn does have storms. Occasionally, massive storms erupt in the atmosphere, creating bright white spots that can be seen from Earth. These storms are rare, occurring roughly once every 30 years, coinciding with Saturn's northern hemisphere summer. The most recent major storm occurred in 2010 and lasted for several months, encircling the entire planet. Saturn also has a hexagonal cloud pattern at its north pole, a bizarre geometric feature that has persisted for decades. The hexagon is about 30,000 kilometers across, larger than two Earths, and it is a standing wave pattern in the jet stream, created by the interaction of winds at different latitudes. The hexagon rotates with the planet, and at its center is a massive hurricane-like vortex. Saturn emits more energy than it receives from the Sun, just like Jupiter. The planet is slowly contracting under its own gravity, and this contraction generates heat. Saturn radiates about 1.8 times as much energy as it absorbs from the Sun, making it a warm world despite its distance. But the most striking feature of Saturn is its rings. The rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. They extend hundreds of thousands of kilometers from the planet but are incredibly thin, only about 10 meters thick in most places. The rings are divided into several main sections, labeled A through G, with gaps between them created by the gravitational influence of Saturn's moons. The rings are ancient, possibly as old as the solar system itself, though some scientists believe they may be younger, formed from the breakup of a moon or comet within the past few 100 million years. The rings are slowly eroding, with particles falling into Saturn's atmosphere due to the planet's magnetic field. At the current rate, the rings may disappear in about 100 million years, a brief moment in cosmic time. There is something ethereal about Saturn. It is a world of quiet beauty, adorned with rings that shimmer in the sunlight. Saturn is the jewel of the solar system, a planet that inspires awe and wonder, a reminder that the universe is capable of creating structures of breathtaking elegance. The rings of Saturn are one of the most iconic sights in the solar system. They are visible from Earth with even a small telescope, appearing as delicate arcs extending from either side of the planet. But up close, the rings are a complex dynamic system, a cosmic ballet of ice and rock orbiting in perfect harmony. The rings are composed of billions of individual particles, each one orbiting Saturn independently. The particles are mostly water ice, with some rocky material mixed in. They range in size from micrometers to meters, with the largest particles being house-sized chunks of ice. The particles are highly reflective, which is why the rings are so bright. The rings are divided into several main sections. The A ring is the outermost major ring, extending from about 122,000 to 137,000 kilometers from Saturn's center. The B ring is the brightest and most massive, extending from about 92,000 to 117,500 kilometers. Between the A and B rings is the Cassini division, a gap about 4,800 kilometers wide, created by the gravitational influence of Saturn's moon Mimas. The C ring is fainter and closer to the planet, extending from about 74,500 to 92,000 kilometers. Inside the C ring is the D ring, a very faint ring that extends down to the planet's cloud tops. Outside the A ring are the F, G, and E rings, which are much fainter and more diffuse. The F ring is particularly interesting. It is narrow and braided, with kinks and clumps that change over time. The structure of the F ring is shaped by two small moons, Prometheus and Pandora, which orbit just inside and outside the ring. These shepherd moons gravitationally confine the ring particles, preventing them from spreading out. The E ring is the largest and most diffuse of Saturn's rings, extending from the orbit of Mimas out to the orbit of Titan, a distance of over 1 million kilometers. The E-ring is supplied by water ice particles ejected from the moon Enceladus, which orbits within the ring. Enceladus sprays water vapor and ice particles into space through geysers at its south pole, and these particles spread out to form the E-ring. The rings are not solid, they are made of countless individual particles, each one following its own orbit around Saturn. The particles collide with each other, clump together, and break apart, creating a constantly shifting pattern. The rings are also influenced by the gravity of Saturn's moons, which create waves and gaps in the ring structure. The rings are incredibly thin. Despite extending hundreds of thousands of kilometers from the planet, they are only about 10 meters thick in most places. If you were to scale the rings down to the size of a piece of paper, they would be thinner than the paper itself. This thinness is maintained by collisions between particles which flatten the ring into a thin disk. The origin of Saturn's rings is still debated. One theory is that they are the remnants of a moon or comet that was torn apart by Saturn's gravity, a process called tidal disruption. Another theory is that they are leftover material from the formation of Saturn, material that never coalesced into a moon. The rings may also be relatively young, formed within the past few 100 million years, though this is still uncertain. There is something mesmerizing about Saturn's rings. They are a cosmic ballet, a dance of ice and rock that has been going on for millions or billions of years. The rings are delicate, ephemeral, and beautiful, a reminder that even in the vastness of space, there is room for elegance and grace. Titan is Saturn's largest moon and the second largest moon in the solar system, only slightly smaller than Ganymede. It has a diameter of 5,150 kilometers, making it larger than the planet Mercury. But what makes Titan truly remarkable is its thick atmosphere, the only moon in the solar system with a substantial atmosphere, and the only place besides Earth where liquid exists on the surface. Titan orbits Saturn at a distance of 1.2 million kilometers, taking 15.95 days to complete one orbit. It is tidally locked to Saturn, always showing the same face to the planet. Titan is far from the Sun, and temperatures on the surface are frigid, around minus 179 degrees Celsius. The atmosphere of Titan is thick, with a surface pressure about 1.5 times that of Earth's. It is composed mostly of nitrogen, about 95%, with the rest being methane and trace amounts of other hydrocarbons. The atmosphere is so thick that it completely obscures the surface in visible light, giving Titan a hazy orange appearance. The orange color comes from complex organic molecules called tholins, created when methane in the upper atmosphere is broken down by ultraviolet light from the sun. The tholins form a thick haze that scatters light, creating the orange glow. This haze extends hundreds of kilometers above the surface, making Titan look like a fuzzy ball. Beneath the haze, the surface of Titan is a world of lakes and rivers, but not of water. The liquid on Titan is methane and ethane, hydrocarbons that are gases on Earth but liquids in Titan's frigid temperatures. Titan has hundreds of lakes, mostly in the polar regions, and several large seas, the largest of which, Kraken Mare, is larger than the Caspian Sea on Earth. The lakes and seas are fed by rivers that flow across the surface, carving channels and creating deltas. Titan also has a methane cycle, similar to Earth's water cycle. Methane evaporates from the lakes, rises into the atmosphere, condenses into clouds and falls as rain. The rain flows across the surface, filling the lakes and seas, and the cycle continues. The surface of Titan is also covered in dunes, vast fields of sand-like particles made of organic compounds. The dunes are hundreds of meters tall and stretch for hundreds of kilometers, shaped by winds in Titan's thick atmosphere. The landscape is alien but strangely familiar, with rivers, lakes, dunes, and mountains, all sculpted by processes similar to those on Earth. Beneath the surface, Titan may have a subsurface ocean of liquid water, kept warm by tidal heating and radioactive decay. This ocean would be buried beneath a thick, icy crust, but it could exist, making Titan another potential habitat for life, though very different from the surface environment. Titan is one of the most intriguing objects in the solar system. It is a world with weather, with seasons, with a landscape that changes over time. It is the only place besides Earth where we have found stable liquid on the surface, and it is a natural laboratory for studying organic chemistry and the conditions that might lead to life. There is something hauntingly beautiful about Titan. It is a world shrouded in haze, a place where methane rains from the sky and fills lakes and seas. Titan is a reminder that the solar system is full of worlds that are both alien and familiar, places that challenge our understanding of what a habitable world can be. Enceladus is a small moon, only about 500 kilometers in diameter, but it is one of the most active and intriguing objects in the solar system. Its south pole is covered in geysers that spray water vapor and ice particles hundreds of kilometers into space, creating a plume that feeds Saturn's E-ring. Enceladus is a world of ice and water, and it may have a subsurface ocean that could harbor life. Enceladus orbits Saturn at a distance of 238,000 kilometers, taking 1.37 days to complete one orbit. It is tidally locked to Saturn, and it experiences tidal heating due to its slightly eccentric orbit and gravitational interactions with other moons. This tidal heating keeps the interior warm, preventing the subsurface ocean from freezing. The surface of Enceladus is bright white, covered in fresh ice that reflects nearly 100% of the sunlight that hits it. This makes Enceladus the most reflective object in the solar system. The surface is divided into two main types of terrain: heavily cratered regions that are ancient, and smooth, tectonically active regions that are young. The most striking feature on Enceladus is the south polar region, which is covered in long parallel fractures called tiger stripes. These fractures are warmer than the surrounding terrain, and they are the source of the geysers. The geysers erupt continuously, spraying water vapor, ice particles, and organic molecules into space at speeds of up to 400 meters per second. The plume from Enceladus has been sampled by the Cassini spacecraft, which flew through it several times. The plume contains water vapor, ice particles, salt, silica, and complex organic molecules, including some that are associated with life on Earth. The presence of salt and silica suggests that the water is in contact with a rocky sea floor where hydrothermal activity could be occurring. Beneath the icy crust, Enceladus is thought to have a global ocean of liquid water, about 10 kilometers deep, buried beneath an ice shell that is about 20 to 25 kilometers thick at the South Pole and thicker elsewhere. The ocean is kept liquid by tidal heating, and it may be in contact with a rocky core where chemical reactions could provide energy for life. The discovery of the plume and the evidence for a subsurface ocean have made Enceladus one of the top targets in the search for life beyond Earth. The plume provides a way to sample the ocean without drilling through the ice, and the presence of organic molecules and energy sources suggests that the ocean could be habitable. There is something hopeful about Enceladus. It is a small moon, far from the sun, but it is geologically active, with geysers that spray water into space. Enceladus is a reminder that even the smallest worlds can be dynamic and interesting, that the conditions for life may exist in unexpected places. Mimas is a small moon, about 400 kilometers in diameter, but it has one of the most distinctive features in the solar system, a massive impact crater called Herschel, which gives Mimas an uncanny resemblance to the Death Star from Star Wars. Mimas is a heavily cratered world, a relic of the violent early solar system. Mimas orbits Saturn at a distance of 186,000 kilometers, taking 0.94 days to complete one orbit. It is the innermost of Saturn's major moons, and its gravity is responsible for creating the Cassini division, the large gap in Saturn's rings. Mimas's gravitational influence clears out particles from the Cassini division through a process called orbital resonance. The surface of Mimas is heavily cratered, covered in impact scars from billions of years of bombardment. The craters range in size from tiny pits to massive basins, and they are well preserved due to the lack of geological activity. Mimas is a cold, dead world, with no signs of internal heat or tectonic activity. The most prominent feature on Mimas is Herschel crater, which is about 130 kilometers across, nearly 1/3 the diameter of the Moon itself. The impact that created Herschel was so powerful that it nearly shattered Mimas. The crater has a central peak that rises about 6 kilometers above the crater floor, and the walls are about 5 kilometers high. On the opposite side of Mimas, there are fractures and disrupted terrain, likely caused by shock waves from the Herschel impact. Mimas is made mostly of water ice, with a small rocky core. The surface is bright and reflective, though not as bright as Enceladus. The ice is old and heavily cratered, and there is no evidence of recent geological activity. Mimas is a frozen relic, a world that has been geologically dead for billions of years. Despite its small size and lack of activity, Mimas plays an important role in the Saturn system. Its gravitational influence shapes the rings, creating gaps and maintaining the structure of the ring system. Mimas is a shepherd moon, quietly influencing the orbits of countless ring particles. There is something stark about Mimas. It is a small, heavily cratered world marked by a single massive impact that nearly destroyed it. Mimas is a reminder of the violence of the early solar system, a world that bears the scars of billions of years of bombardment. Saturn has at least 146 known moons, making it the planet with the most moons in the solar system. Most of these moons are small, irregular objects, likely captured asteroids or comets, but several of the larger moons are worlds in their own right, each with unique features and histories. Rhea is the second largest moon of Saturn, about 1,530 kilometers in diameter. It is heavily cratered with a bright, icy surface. Rhea may have a tenuous ring system of its own, though this has not been confirmed. It is a quiet, geologically inactive world, similar to Callisto. Iapetus is one of the most bizarre moons in the solar system. It has a two-tone appearance, with one hemisphere bright white and the other dark as coal. The dark material is thought to be organic compounds, possibly from the moon Phoebe, which orbits farther out and sheds dark material that Iapetus sweeps up. Iapetus also has a massive equatorial ridge that circles the moon, giving it a walnut-like appearance. Dione is another icy moon, about 1,120 kilometers in diameter. It has a heavily cratered surface, but it also shows evidence of past geological activity, with bright, wispy streaks that may be ice cliffs or fractures. Dione may have a subsurface ocean, though this is uncertain. Tethys is similar in size to Dione, about 1960 kilometers in diameter. It has a massive impact crater called Odysseus, which is about 400 kilometers across, nearly half the diameter of the Moon. Tethys also has a large canyon system called Ithaca Chasma, which stretches for over 2,000 kilometers. Hyperion is a small, irregularly shaped moon with a sponge-like appearance. Its surface is covered in deep craters, and the moon tumbles chaotically in its orbit with no stable rotation. Hyperion is thought to be a fragment of a larger object that was broken apart by a collision. Phoebe is an irregular moon that orbits Saturn in a retrograde direction, opposite to the other moons. It is thought to be a captured object from the Kuiper belt. a region beyond Neptune filled with icy bodies. Phoebe is dark and heavily cratered, and it may be the source of the dark material on Iapetus. There is something wonderful about Saturn's diverse family of moons. Each one is unique, with its own history, its own features, its own story. They are a reminder that the solar system is full of variety, that no two worlds are exactly alike. Beyond Saturn, the solar system grows darker and colder. The sun is a distant point of light, and the worlds here are frozen, mysterious, and strange. This is the realm of the ice giants, Uranus and Neptune, and the distant dwarf planets that orbit in the outer darkness. These are the edge worlds, the final outposts of our solar system, the places where sunlight fades and the cold of interstellar space begins to seep in. Tonight we complete our journey through the solar system, visiting these distant wanderers and contemplating our place in this vast cosmic neighborhood. Uranus is the seventh planet from the Sun, orbiting at an average distance of 2.9 billion kilometers. It takes 84 Earth years to complete one orbit, moving so slowly through the sky that ancient astronomers did not recognize it as a planet. Uranus was the first planet discovered with a telescope, found by William Herschel in 1781, doubling the known size of the solar system overnight. Uranus is an ice giant, smaller than Jupiter and Saturn, but still massive, with a diameter of 50,724 kilometers, about 4 times the diameter of Earth. Unlike the gas giants, which are made mostly of hydrogen and helium, Uranus is composed primarily of water, methane, and ammonia ices, with a small rocky core. The methane in the atmosphere absorbs red light, giving Uranus its distinctive blue-green color. But the most remarkable thing about Uranus is its tilt. The planet's axis is tilted 98 degrees relative to its orbital plane, meaning it essentially rolls around the Sun on its side. The north and south poles of Uranus point almost directly at the Sun at different times in its orbit. This extreme tilt means that each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The cause of this tilt is unknown, but the most likely explanation is a massive collision early in the planet's history. A large object, perhaps the size of Earth, may have struck Uranus with enough force to knock it onto its side. The planet has remained tilted ever since, a permanent reminder of that ancient impact. Uranus rotates relatively quickly, completing one rotation in about 17 hours. This rapid rotation, combined with the extreme tilt, creates unusual seasonal patterns. The atmosphere is mostly hydrogen and helium, with about 2% methane. The methane gives Uranus its color and also creates a haze in the upper atmosphere. The atmosphere of Uranus is calm compared to Jupiter and Saturn. There are few visible storms or cloud features, and the planet appears almost featureless in visible light. But observations in other wavelengths reveal a more dynamic atmosphere, with bands of clouds and occasional storms. The lack of internal heat, Uranus emits very little more energy than it receives from the Sun, may explain why the atmosphere is so calm. Uranus has a magnetic field, but it is unusual. The field is tilted 59 degrees relative to the planet's rotation axis, and it is offset from the center of the planet. This creates a lopsided magnetosphere that wobbles as the planet rotates. The magnetic field is thought to be generated in a layer of superionic water deep in the interior, where water molecules are broken apart under extreme pressure and temperature. Uranus has a faint ring system, discovered in 1977. The rings are narrow and dark, made of particles that are much darker than Saturn's bright ice rings. The rings are thought to be relatively young, formed from the breakup of moons or captured objects. Uranus also has 27 known moons, most of them small and irregularly shaped. named after characters from the works of William Shakespeare and Alexander Pope. There is something lonely about Uranus. It is a tilted world, rolling through space on its side, far from the Sun, with a calm, featureless atmosphere and a lopsided magnetic field. Uranus is a reminder that the outer solar system is a strange and alien place, where the familiar rules of the inner planets no longer apply. Neptune is the eighth and outermost planet in the solar system, orbiting at an average distance of 4.5 billion kilometers from the Sun. It takes 165 Earth years to complete one orbit, meaning it has completed only one full orbit since its discovery in 1846. Neptune is so far from the Sun that it receives only about 1,000th the sunlight that Earth receives, yet it is one of the most dynamic planets in the solar system. Neptune is similar in size and composition to Uranus, with a diameter of 49,244 kilometers. It is an ice giant, made mostly of water, methane, and ammonia ices, with a small rocky core. Like Uranus, Neptune's atmosphere contains methane, which absorbs red light and gives the planet its deep blue color. But Neptune is a darker, richer blue than Uranus, possibly due to an unknown component in the atmosphere. Neptune is a world of powerful winds. The atmosphere is incredibly dynamic, with winds reaching speeds of up to 2,100 kilometers per hour, the fastest in the solar system. These winds blow in the opposite direction to the planet's rotation, creating a retrograde jet stream that circles the planet. The source of energy for these winds is a mystery, as Neptune receives so little sunlight. Neptune emits more than twice as much energy as it receives from the Sun, indicating a strong internal heat source. This internal heat drives the atmospheric dynamics, creating storms and cloud features that are visible even from Earth. The most famous feature was the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, observed by Voyager 2 in 1989. The Great Dark Spot has since disappeared, but other storms have appeared, showing that Neptune's atmosphere is constantly changing. Neptune rotates in about 16 hours, creating a rapid day-night cycle. The atmosphere is divided into bands, with bright clouds of methane ice crystals floating high above darker regions. The clouds cast shadows on the layers below, creating a three-dimensional structure that is visible in high-resolution images. Neptune has a magnetic field similar to Uranus's, tilted 47 degrees relative to the rotation axis and offset from the center. This creates a complex, asymmetric magnetosphere that interacts with the solar wind in unusual ways. The magnetic field is thought to be generated in a layer of superionic water, similar to Uranus. Neptune has a faint ring system discovered in the 1980s. The rings are narrow and clumpy, with some sections much brighter than others. The rings are made of dark particles, possibly organic compounds, and they are thought to be relatively young. Neptune also has 14 known moons, the largest of which is Triton. There is something majestic about Neptune. It is a world of deep blue, of powerful winds, of dynamic storms, a planet that defies expectations. Neptune is far from the Sun, yet it is one of the most active planets in the solar system, a reminder that distance does not mean stillness. Triton is Neptune's largest moon, and it is one of the most unusual moons in the solar system. It orbits Neptune in a retrograde direction, opposite to the planet's rotation, and it is slowly spiraling inward, doomed to be torn apart by tidal forces in a few billion years. Triton is a captured object, likely a dwarf planet from the Kuiper Belt, that was pulled into orbit by Neptune's gravity. Triton is large, with a diameter of 2,706 kilometers, making it the seventh largest moon in the solar system. It is slightly smaller than Earth's moon, and it is the only large moon in the solar system with a retrograde orbit. This retrograde orbit is strong evidence that Triton did not form with Neptune, but was captured later. The surface of Triton is young and geologically active, with very few impact craters. It is covered in nitrogen ice, with regions of methane and carbon dioxide ice. The surface is crisscrossed with fractures and ridges, and there are large, smooth plains that may be frozen lakes of liquid nitrogen. The surface is also covered in a pinkish material, possibly organic compounds created by radiation. Triton has active geysers that erupt from the surface, spraying nitrogen gas and dark particles several kilometers into the thin atmosphere. These geysers are thought to be driven by solar heating of subsurface nitrogen ice, which vaporizes and erupts through cracks in the surface. The dark particles fall back to the surface, creating dark streaks that are visible in images. Triton has a thin atmosphere composed mostly of nitrogen, with traces of methane. The atmospheric pressure is only about 1/70,000th of Earth's, making it one of the thinnest atmospheres in the solar system. The atmosphere is slowly escaping into space, stripped away by Neptune's magnetosphere and the solar wind. Triton is incredibly cold, with surface temperatures around -235 degrees Celsius, making it one of the coldest objects in the solar system. Despite the cold, Triton is geologically active, with evidence of cryovolcanism and tectonic activity. The Moon may have a subsurface ocean of liquid water, kept warm by tidal heating as it spirals inward toward Neptune. Triton's capture by Neptune was likely a violent event. The Moon's orbit would have been highly elliptical at first, and tidal forces would have circularized the orbit over time, generating enormous amounts of heat. This heat may have melted Triton's interior, resurfacing the Moon and erasing the ancient craters. The capture may also have disrupted Neptune's original moon system, scattering or destroying the moons that existed before Triton arrived. There is something tragic about Triton. It is a captured world, torn from its original orbit and pulled into a slow death spiral around Neptune. In a few billion years, Triton will cross the Roche limit, the distance at which tidal forces will tear it apart, and it will be destroyed, forming a spectacular ring system around Neptune. But for now, Triton endures, a geologically active world in the outer darkness. Pluto was once considered the 9th planet, but in 2006 it was reclassified as a dwarf planet, a decision that sparked debate and captured public imagination. Pluto orbits the Sun at an average distance of 5.9 billion kilometers, taking 248 Earth years to complete one orbit. It is a small, icy world, part of a vast population of objects in the Kuiper Belt, the region beyond Neptune. Pluto has a diameter of about 2,377 kilometers, smaller than Earth's moon. It is made mostly of rock and ice, with a surface covered in nitrogen, methane, and carbon monoxide ices. The surface is varied, with bright plains, dark regions, and towering mountains made of water ice, which is as hard as rock at Pluto's frigid temperatures. The most famous feature on Pluto is Tombor Regio, a large, bright, heart-shaped region informally known as Pluto's heart. The western lobe of the heart, Sputnik Planitia, is a vast plain of nitrogen ice, smooth and crater-free, indicating recent geological activity. The nitrogen ice is slowly flowing, like a glacier, driven by convection currents in the ice. Pluto has a thin atmosphere composed mostly of nitrogen with traces of methane and carbon monoxide. The atmosphere is only present when Pluto is near perihelion, the closest point in its orbit to the Sun. As Pluto moves away from the Sun, the atmosphere freezes and falls to the surface as frost, then sublimates again when Pluto returns to perihelion. Pluto has 5 known moons, the largest of which is Charon. Charon is about half the size of Pluto, making the Pluto-Charon system more like a double dwarf planet than a planet and moon. Pluto and Charon are tidally locked to each other, meaning they always show the same face to each other, orbiting a common center of mass that lies between them. The New Horizons spacecraft flew by Pluto in 2015, providing the first close-up images of the dwarf planet. The images revealed a world far more complex and geologically active than anyone expected. Pluto has mountains, glaciers, dunes, and possibly even cryovolcanoes. The surface is young in some areas with no impact craters, suggesting ongoing geological processes. The discovery of Pluto's complexity challenged the idea that small, distant worlds are geologically dead. Pluto is far from the Sun, receiving almost no sunlight, yet it is active with a dynamic surface and a thin atmosphere. The source of energy for this activity is still debated, but it may involve radioactive decay in the core or tidal heating from interactions with Charon. There is something endearing about Pluto. It is a small world far from the Sun, but it is complex and active, with a heart-shaped region that has captured the imagination of millions. Pluto is a reminder that even the smallest, most distant worlds can surprise us, that the solar system is full of wonders waiting to be discovered. Beyond Neptune lies the Kuiper Belt, a vast region of icy objects that extends from about 30 to 55 astronomical units from the Sun. The Kuiper Belt is similar to the asteroid belt, but it is much larger and contains mostly icy bodies rather than rocky ones. It is home to thousands of known objects, including dwarf planets, comets, and countless smaller bodies. The Kuiper Belt is a relic of the early solar system, a region where the material never coalesced into a planet due to the low density and the gravitational influence of Neptune. The objects in the Kuiper Belt are pristine, largely unchanged since the solar system formed 4.6 billion years ago. They are time capsules, preserving the conditions of the early solar system. The largest known objects in the Kuiper Belt are dwarf planets. Besides Pluto, there are several others, including Eris, Makemake, and Haumea. Eris is slightly smaller than Pluto, but more massive, and its discovery in 2005 was one of the factors that led to Pluto's reclassification. Makemake is about 2/3 the size of Pluto, and Haumea is elongated, shaped like a football, possibly due to a massive impact. The Kuiper Belt is also the source of short-period comets that orbit the Sun in less than 200 years. These comets originate in the Kuiper Belt and are occasionally perturbed by Neptune's gravity, sending them into the inner solar system. As they approach the Sun, the ice sublimates, creating the characteristic tail. The Kuiper Belt is difficult to study because the objects are small, distant, and faint. Most of what we know comes from ground-based telescopes and the New Horizons spacecraft which flew through the Kuiper Belt after its Pluto flyby. In 2019, New Horizons visited a Kuiper Belt object called Arakoth, a contact binary formed from two lobes that gently merged together. Arakoth is one of the most pristine objects ever studied, with a smooth, lightly cratered surface and a reddish color from organic compounds. It formed through gentle collisions in the early solar system, and it has remained largely unchanged for billions of years. Arakoth is a snapshot of the conditions in the early solar system, a frozen relic from the dawn of time. There is something peaceful about the Kuiper Belt. It is a frozen frontier, a region of ancient, pristine objects drifting in the darkness. The Kuiper Belt is a reminder that the solar system extends far beyond the planets, that there are vast regions of space filled with icy bodies quietly orbiting the Sun. Beyond the Kuiper Belt, at the very edge of the solar system, lies the Oort cloud, a vast spherical shell of icy objects that extends from about 2,000 to 100,000 astronomical units from the Sun. The Oort cloud is so distant that it is halfway to the nearest star. It is the source of long-period comets, comets that take thousands or even millions of years to orbit the Sun. The Oort cloud has never been directly observed. It is too distant and too faint for current telescopes to detect, but its existence is inferred from the orbits of long-period comets which come from all directions in the sky, suggesting a spherical distribution of objects surrounding the solar system. The Oort cloud is thought to contain trillions of icy bodies, ranging in size from a few kilometers to hundreds of kilometers across. These objects are the remnants of the early solar system, material that was ejected from the inner solar system by the gravity of the giant planets. They have been drifting in the outer darkness for billions of years, barely influenced by the Sun's gravity. Occasionally, a passing star or a gravitational disturbance will nudge an Oort cloud object, sending it on a long journey toward the inner solar system. As it approaches the Sun, the ice begins to sublimate, and the object becomes a comet with a glowing coma and a long tail. These comets are visitors from the edge of the solar system, messengers from the Oort cloud. The Oort cloud marks the boundary of the solar system, the edge of the Sun's gravitational influence. Beyond the Oort cloud lies interstellar space, the vast emptiness between the stars. The Sun's light is faint here, and the stars are bright, no longer obscured by the Sun's glare. This is the edge of home, the place where the solar system ends and the galaxy begins. Our journey through the solar system is complete. We have travelled from the Sun, through the rocky inner planets, past the gas giants and ice giants, to the frozen dwarf planets and the distant Kuiper belt. We have visited dozens of moons, explored rings and asteroids, and contemplated the vast distances that separate these worlds. The solar system is our neighbourhood, a collection of worlds bound together by gravity, all orbiting the same star. It is a place of incredible diversity, with worlds of fire and ice, of gas and rock, of oceans and deserts. Each world is unique, each has its own story, and together they form a cosmic family. We are part of this family. Earth is our home, but the solar system is our neighbourhood. The Sun warms us, the Moon steadies us, and the planets orbit in silent harmony. We are travellers on a quiet blue ship, moving through space at cosmic speeds, yet feeling only stillness. Take a slow breath. Feel the ground beneath you, solid and stable, yet moving at thousands of kilometers per hour. You are here, now, on Earth, part of the solar system, part of the galaxy, part of the universe. You are home. Sleep well, traveller. The silent neighbours watch over us all,